Okay, so hi everybody, welcome back. Today we're going to be finishing up our chapter 14 lecture on oscillations. So by the end of this video, we'll be completely finished with chapter 14 and all the content that I wanted to cover dealing with oscillations. So the last bit to cover is energy losses and driving forces in harmonic motion. So far, when we've dealt with an oscillating system, we've assumed that it doesn't lose any energy due to things like friction and air resistance. So now we're going to relax that assumption and see what happens when an oscillating system loses energy. We're also going to take a look at driving forces, which are outside forces acting on the system as it oscillates. Okay, so these are the two things we're going to cover in this video. Okay. So we'll start with damped harmonic motion. So again, up until this point, we've really only been considering oscillating systems that do not lose mechanical energy over time. Now, that's not exactly realistic because in any real-world system, you're going to have forces like friction and air resistance acting on your system, and they will tend to remove mechanical energy or decrease the mechanical energy of the system and convert it into things like heat. So we need a way of accounting for things like friction and air resistance in a system and the way that they take energy out of the system. So when we do this, the result is called damped harmonic motion. Okay, so in order to be able to deal with damped harmonic motion, we need some kind of formula for the force that removes mechanical energy from an oscillating system. So let's start with this. This is the equation for a drag force. And basically a drag force is what you get when you have an object moving through a fluid. So if you have an object moving through the air, we'll get what's called air resistance, and that's an example of a drag force. But it's not just limited to that. If you have an object moving through water, let's say, the water is going to exert a force on the object, which opposes its motion. That would, again, be an example of a drag force. So in general, when you have an object moving through a fluid, the fluid will exert a drag force on the object. So how is that drag force described? Well, if the object is relatively small and the speed that it's moving is relatively small also, the drag force is going to be given by this equation. So this is what we'll be using throughout what comes next. Fd, the drag force, is minus b times v. The negative sign here indicates that the drag force opposes the motion because it's in the opposite direction as the velocity. So if this is our object moving through this fluid here, if the velocity is to the right, then the drag force will be opposing that motion and it will be going to the left. So in that sense, it's a lot like friction. It's a force that opposes the motion. Now, we have a constant in this equation, b. Now, b depends on various properties of the fluid and the object. So it depends on how dense the fluid is. It depends on how aerodynamic the object is. We're not going to concern ourselves with those details. We're just going to say it's all wrapped up in a constant which we call b. And then finally, v is, of course, the velocity of the object relative to the fluid. So if you take the constant b times v with a negative sign out front to indicate we're opposing the motion with this force, then we have a description of a drag force. So basically what we're going to do is introduce this force into an oscillating system and see. So to get a sense of how the equations for damped harmonic motion are developed, let's take the example of the mass on a spring. So we have a block mass m connected to a spring whose force constant is k. And that block is able to move back and forth along some sort of surface. But now we're going to imagine that there's a drag force acting on the block in addition to the spring force. So remember, x equals 0 represents the equilibrium position of the spring. And we use x to keep track of where the block is at any given time. So let's say that in this picture, we're looking at a snapshot of the system where the block is located right here, and it's moving to the left. So its velocity is to the left. Well, the drag force, if you remember, always is going to oppose the velocity, so that's going to be pointing to the right. And since x is positive, in other words, the spring is being stretched out in this situation, x is greater than 0, that means the spring force is going to be going in the negative direction. It's going to the left. Okay, so that's the direction of both of these forces, just at the snapshot in time that we're seeing in this picture. So in general, the drag force acting on the block is going to be given by minus b times vx. The negative sign indicates that the drag force is in the opposite direction as velocity. And the spring force is given by Hooke's law, so the spring force is minus kx. And those will be the two forces acting on the block in the x direction. So if we apply F equals ma, Newton's second law, in the x direction, here's what we'll get. Those two forces, again, that we add together on the left side of the equation are minus kx and minus b times vx. That should equal m times ax. But also remember that when it comes to velocity, this is the first derivative of position with respect to time. And acceleration, that's the second derivative of position with respect to time. So let's make those substitutions here and here for velocity and acceleration. So we have minus kx, then minus b times dx dt, again, that's the first derivative, equals m times the second derivative of x with respect to time. That's what we sub in for acceleration. So to write this in a more standard form, we simply take these two negative terms and move them over to this side by adding them. And so what we get is m times the second derivative of x with respect to time, plus b times the first derivative of x with respect to time, plus k times x is equal to 0. And this is the differential equation that we need to solve if we want to find the position of the block as a function of time. So the differential equation has changed now that we have this damping force to account for in the equation. So if we want to solve this differential equation, there are all sorts of fancy methods we could use, but the simplest thing to do is called the guess and check method. In other words, we're going to guess a solution for x as a function of time. We're going to plug it in, and then we'll check to see that it actually solves the differential equation. So let's try this out as a solution. We have x as a function of time equals a0 times e to the minus gamma t times cosine omega prime times t. So here, a0 represents an amplitude, just like before. And in the cosine function, we're going to set the phase, the phi, equal to 0, just for simplicity. And gamma that you see in the exponent here in this solution is just going to be some constant. Okay? So we have three different constants in the equation. We have a naught, we have gamma, and we have omega prime. So again, let's plug this into the differential equation and just verify that it works as a solution. Okay, so we'll start with the initial guess at the solution, which is x as a function of time equals a naught times e to the minus gamma t times cosine omega prime t. So the first thing we'll do is find the derivative of this function, dx dt. So in order to do this, we have to realize what we have here is a product of two functions. We have the exponential, e to the minus gamma t, and then we have the cosine omega prime t function. And we have the product of the two, so in evaluating the derivative, we would use the product rule. So let me just remind you how this works. So let's call this function number 1, function number 2. To evaluate the derivative using the product rule, we take the derivative of number 1, and then we just multiply that by, derivative of number 1, and then we just multiply that by number 2, and then we add that to just number 1 left alone times the derivative of number 2. That's how the product rule works in general. Okay, so with that in mind, the derivative of the function we have here is, so we have a naught as a constant out front. Then we take the derivative of the first function, which is minus gamma times e to the minus gamma t. So in other words, we bring out a factor of minus gamma when we take the derivative of the first function. And then we just multiply by the second one, cosine omega prime t, just left alone. Then we add to that, so we have the constant a naught out front. And then we have e to the minus gamma t. We're just leaving function number 1 alone now. And then we have to take the derivative of the second function. So cosine, when you take the derivative, goes to negative sine. But then we bring out a factor of omega prime when we do that derivative. Okay? So let's do this one more time. We have the second derivative of x with respect to time. So we have to be careful now. We're doing the product rule twice. So we're going to do it once for the first term, and then we're going to do it again for this second term. Okay, so let's focus on the first term. We have minus a naught times gamma out front already. And then if we take the derivative of this first guy, this first term, we're going to get another factor of minus gamma coming out. So we'll have gamma squared, and this minus sign will become positive. And then we'll have e to the minus gamma t. And then the second term, cosine omega prime t, is just left alone. Okay, next, we're going to have minus a naught times gamma, constants out front. We're going to take the first term, e to the minus gamma t, and leave it alone. And then we'll take the derivative of the second, which is, again, the derivative of cosine omega prime t. So that cosine function becomes sine. It actually becomes negative sine, so we get a negative sign out front, which cancels with this one, making it positive. And we also get a factor of omega prime coming out to the front. Okay, so now we're going to be dealing with, we're going to be dealing with this second term here, okay? So we have minus a naught times omega prime already. If we take the derivative of e to the minus gamma t, we get minus gamma coming out to the front. So the negative sign becomes positive, and we get a factor of gamma out front. And then we have e to the minus gamma t times sine omega prime t, just left alone. Okay, and then finally, we have minus a naught times omega prime. We're going to leave the first function alone, so we have e to the minus gamma t, just leave it alone. And then we'll take the derivative of the second function, which is sine omega prime t. When you take the derivative of that, becomes cosine omega prime t. But we also bring out a factor of omega, so now we have omega prime squared out front. So that's the second derivative. It has these 4 different terms in it. So what do we do with all this? We plug it in into the differential equation. Which, to remind you, says m times the second derivative of x with respect to time plus b times the first derivative of x with respect to time plus k times x equals 0. So, okay, let's do that. Let's plug everything in. So we have 0 equaling a huge mess. The first term is going to be m times the second derivative, which, by the way, is all this right here. To make it a little simpler, let's realize that we have a common factor of a naught e to the minus gamma t in every single term. So we'll pull that common factor out. And then the first term is going to be gamma times cosine omega prime t from this guy. The next one is going to be gamma times omega prime times sine omega prime t from this guy. The third term is going to be omega prime times gamma times sine omega prime t. And then finally, we're going to have minus omega prime squared times cosine omega prime t. So that's the second derivative multiplied by m. The next term is b times the first derivative, which is up here, this guy. So it has two terms in it. And notice how, again, there's a common factor of a naught times e to the minus gamma t, so we'll pull that out. And then we'll have minus gamma times cosine omega prime t from this guy. And then we'll have minus omega prime times sine omega prime t from this guy. And those are the only two terms, so we'll move on to k times x. So we'll have plus k. X was the original function that we're guessing, which is a naught e to the minus gamma t times cosine omega prime t. Okay, so to make this simple, or simpler, we can divide out a naught e to the minus gamma t, because that appears in every single term. So get rid of it here, here, and here. And then we're going to group things by sine and cosine. So notice that everything we're left with is either multiplying a sine function or a cosine function. So how about we put all the cosine stuff together, and then we put all the sine stuff together. So we have 0 equals cosine omega prime t. So let's try to find everything that's multiplying cosine omega prime t. So the first thing I can notice is right here, I have an m times a gamma squared from that term. Okay, I have this term over here, which is minus m times omega prime squared. This is another term with a cosine in it, minus b times gamma. And then finally, this term is just multiplying k. All right, next, what are all the sine terms? We have sine omega prime t. We have this term and this term, which basically are the same thing. So we can group them together and say it's 2 times, we have an m out front over here, and then we have a gamma times omega prime. Now the other sine term that appears is right there, which is minus b, which is out front, times omega prime. Okay, now we're getting somewhere, because if this is going to work as a solution, the entire right-hand side of the equation has to equal 0. So the solution will work as long as both terms in brackets are equal to 0. Okay, so I'm talking about this guy right here. Let's label this number 1. And also this guy right here, number 2. They both have to equal 0 in order for the net result to equal 0. So if we take a look at that second term in brackets, set that equal to 0, we have 2 times m times gamma times omega prime minus b times omega prime equaling 0. Omega prime is a common factor, so we can pull it out. Omega prime times 2 times m times gamma minus b is equal to 0. So in other words, we can have omega prime equals 0, meaning the thing is just not even oscillating, or the thing in the parentheses here is equal to 0, which means 2 times m times gamma minus b equals 0, or 2 times m times gamma is equal to b, or gamma, this constant, is equal to b over 2m. So that's an important result right there. This constant gamma, if this solution is going to work, has to be equal to b divided by 2m. Okay, now let's take the first term in brackets and set that equal to 0. So we have m times gamma squared minus m times omega prime squared minus b times gamma plus k is equal to 0. Okay, let's rearrange this a little bit. Let's add m times omega prime squared to both sides. So m times omega prime squared is equal to m times gamma squared minus b times gamma plus k. And then let's divide out the mass. So omega prime squared is equal to gamma squared minus b over m times gamma plus k. Okay, and now let's plug in what we know gamma is equal to. Omega prime squared is equal to gamma, which is b over 2m squared, minus b over m, times gamma, which is b over 2m, and then plus k. Oops, I forgot to divide k by m earlier. So here, let me correct that. That last term should be k over m, of course, because we divided out the mass. Okay, so to simplify that, we have omega prime squared equals b squared over 4m minus b squared, sorry, I should have said b squared over 4m squared, minus b squared over 2m squared, that's the second term, plus k over m. So omega prime squared is equal to, when I combine these two guys, I just get minus b squared over 4m squared. Okay, so that's that term. And then I have k over m. So I have k over m minus b squared over 4m squared. So to round this off, we have omega prime equals the square root of k over m minus b squared over 4m squared. Okay, so that's the other result we wanted to show. So in order for this solution to work, we need gamma to equal what we found over here in this box, and we need omega prime to equal this. But as long as that's the case, this works as a solution, and this is how a damped harmonic oscillator will behave. Okay, so that was admittedly a little bit painful to go through all that, but now that we've done it, we know the result, and the result is this works as a solution for the damped harmonic oscillator. And furthermore, we know what the constants are, gamma and omega prime, in order for the solution to work. Again, gamma has to be b over 2m, and omega prime has to be the square root of k over m minus b squared over 4m squared. Okay, so that's what we've got for the damped harmonic oscillator. Okay, now that we have this result for omega prime, we can take a closer look at it and use that result to understand how we can have different types of solutions for damped harmonic motion. So the idea here is when we have damping, the frequency of the oscillations is given by this formula. Omega prime is the frequency, which is the square root of k over m minus b squared over 4m squared. So this is telling us again how fast our system is oscillating when we have a damping force. Notice how it's an altered version of the equation we had for no damping, where the frequency is just given by the square root of k over m. So remember, the undamped frequency when we have no friction, no air resistance, is the square root of k over m. So let's call that omega naught. The undamped frequency is the square root of k over m. That's what we have here. And also, let's call this thing gamma that we derived before and we saw was equal to b over 2m. Let's call that the damping coefficient. So notice how in the formula for omega prime, we have omega naught squared right here, and then we have gamma squared right here. So basically, we can write this in a simpler way. Omega prime, which is the frequency of the oscillations with damping, is equal to the square root of omega naught squared, where this is the undamped frequency, minus gamma, which is the damping coefficient. So basically, gamma tells you how important damping is. If it's a large value, then there's a lot of damping. If it's a small value, then there's not that much. So when we look at this formula then, we can see that there are three different types of solutions that we can get. The first one is if omega naught, the undamped frequency, is greater than gamma, which is our damping coefficient. That means this term is going to be greater than this term, and overall we're going to have a positive number under the square root. If you've got a positive number under the square root, then omega prime is just a real number. On the other hand, if omega naught is equal to gamma, then when we subtract these two, we get 0. And what we call this is the critically damped solution. Okay? That's when omega naught is exactly equal to gamma. Now, we can also imagine a case where gamma is bigger than omega naught. So think about that. We're subtracting these two numbers, and if the second one is bigger, then overall we get a negative number under the square root. When you have a negative number under the square root, that's called an imaginary number. So this is a very different type of solution. It's called the overdamped solution. Okay? So these are the three cases. Okay, we have underdamped, critically damped, and overdamped. So now that we have an idea that there are these three different types of solutions, let me show you what they look like when we plot them all out. Okay? So the underdamped solution looks like this. It's shown in blue. We basically have some oscillations happening, but the amplitude of those oscillations are dying out. In other words, the amplitude starts at some value A naught, but then gets smaller over time, and it exponentially decays away over time. When it comes to the critically damped solution, that's the one shown in green, we don't even actually have any oscillations. We just start at some amplitude, and then we just decay away from there without oscillating up and down. For the overdamped solution, it's the same deal. We start at some amplitude, and then we just decay to 0 without oscillating up and down on the way to 0. So again, the difference between these different types of solutions is for underdamped, we have the system oscillating about an equilibrium position while the amplitude decays away. And then when it comes to the critically damped or the overdamped solutions, the system just goes straight to equilibrium, goes straight to 0 without oscillating in the first place. Okay, so that's just a visual representation of those three different types of solutions. Okay, so immediately we can see that there are some engineering applications for damped harmonic motion, and the different types of damped harmonic motion are relevant depending on what you're trying to build. So some systems are designed so that the oscillations die out as quickly as possible. And if you're trying to get oscillations to die out as quickly as possible, you're going to want overdamping or critical damping, meaning gamma, the damping coefficient, is greater than or equal to omega naught, which is the undamped frequency. And an example of this would be the shock absorbers in your car's suspension system. So the idea is if you hit a bump in the road, you don't want your car to bounce up and down for 10 minutes after you hit that bump. Instead, you want the oscillations to die away as quickly as possible. So these shock absorbers are designed to give you overdamping or critical damping, okay? On the other hand, sometimes systems are designed so that the oscillations will persist for as long as possible. You want the oscillations to last for as long as possible. So in this case, you want the smallest amount of damping that you can get, in which case you want omega naught to be a lot bigger than gamma. You want the damping coefficient to be really small. So an example of that would be the pendulum on a grandfather clock. You want this thing to be swinging back and forth for as long as possible, so you don't have to keep winding up the clock over and over again. You want it to just keep going on its own for as long as possible. So you want smallest amount of damping you can get. So that's what we call underdamped. So now let's get into some of the energy considerations when it comes to damped harmonic motion. So if we don't have any damping, we have no friction, no air resistance, then the total mechanical energy, E, is going to be conserved. But of course, if we do have damping, then energy is not conserved, okay? Because the oscillations are dying out. That mechanical energy is being lost, and it's being converted to things like heat. So remember, the solution we have for a damped harmonic oscillator generally looks like this. We have x of t is equal to a naught times e to the minus gamma t times cosine omega prime t. So if we look at the factor in front of the cosine function, that's the amplitude of the oscillations. So a naught times e to the minus gamma t, that is the amplitude. And it's not just a constant amplitude, it's actually an exponentially decaying amplitude, as indicated by the exponential function multiplying a naught. So we have an amplitude exponentially decaying over time, and basically the larger the value of gamma, the faster the amplitude is decaying. Okay, the smaller the value of gamma, then the slower the amplitude will decay over time. So what we can say about the amplitude is it's a function of time equal to a naught times e to the minus gamma t. A naught is just the starting amplitude. Okay, so remember the total mechanical energy of a simple harmonic oscillator depends on the amplitude. So if the amplitude is decaying over time, then the energy should also be decaying over time. Remember, E is equal to 1/2 k times a squared. So if we plug this in for A, what we'll get is the energy equals 1/2 times k, and then we'll have a naught squared, and then we'll have e to the minus 2 times gamma t, because if you square the exponential, you're going to get a factor of 2 in the exponential. So what this is telling us is the energy is a function of time, which is exponentially decaying. Okay, the energy is going away. So with that in mind, with this result in mind, let's do an example. Let's say we have a damped harmonic oscillator that has a damping coefficient of gamma equal to 0.0135 inverse seconds. Let's say that at t equals 0, the oscillator is set into motion. At what time, t in seconds, does the mechanical energy fall to 50% of its initial value? And then as a follow-up to that, at what time does the mechanical energy fall to 10% of its initial value? So pause the video, try to work this out using the result we derived, and then come back to the video so we can go through it together. Okay, so here's what we have. The energy, the total mechanical energy of the oscillator, E, as a function of time, is equal to 1/2 times K times A naught squared times E to the minus 2 times gamma times T. Now let's take a look at this term out front. This is a constant because K and A naught are both constants. And this constant equals the initial mechanical energy of the system, in other words, at T equals 0. Okay? So why don't we just call this constant E naught for the mechanical energy when T is equal to 0. And by the way, verify this. If you plug in 0 for the time, you're going to get 1/2 times K times A naught squared times E to the 0 power, because we're plugging in 0 for the time. E to the 0 is just 1. So this is 1/2 K A naught squared. That's what we're calling the initial energy, E naught. So to simplify, the energy at time T is equal to that initial energy E naught times E to the minus 2 times gamma times T. So the first question asks if we're at 50% of initial energy, basically what is the time? So what we'll do is on the left side of the equation, we'll set the energy equal to 0.500 E naught, so exactly half of the initial energy, or 50%. That equals E naught times E to the minus 2 times gamma times T. So it actually doesn't matter what the actual value of E naught is, that drops out. Next thing we'll do, since we're trying to find T, is take the natural log on both sides. So we'll have the natural log of 0.500 over here. On the other side, if we take the natural log of E to the minus 2 times gamma T, remember, if you take the natural log of an exponential, you just undo the exponential. So we have natural log of 0.500 equaling minus 2 gamma T. So T is going to be minus natural log of 0.500 divided by 2 times gamma. And that's going to be the time we're looking for. So we have minus natural log 0.500 divided by 2 times gamma, which is 0.0135 inverse seconds. So seconds goes to the top. So we have an amount of time in seconds. And if you calculate this, you'll get 25.67 seconds, which rounds to about 25.7 seconds. So after 25.7 seconds, this oscillator, the energy has been reduced to 50% of its initial energy. Okay. So the second question is basically the same thing, except now we're at 10% of initial energy. And then the question is, again, what is T? So here, we're going to set up the equation in the same exact way. Remember, the energy at time T, which is going to be 0.100 times E naught, So it's only 10% of what we started with. That equals E naught times e to the minus 2 times gamma times t. Once again, E naught goes away. We'll take the natural log of both sides. Natural log 0.100 equals minus 2 times gamma t. And we take the natural log of the exponential. Again, we undo it. And then t is equal to minus natural log 0.100 over 2 gamma, which is equal to minus natural log 0.100 over 2 times gamma is 0.0135 inverse seconds again. So if you crunch those numbers, you get 85.28, keep 3 sig figs again, seconds. So it takes 85.3 seconds for the oscillator to fall to 50%, or sorry, to 10% of its initial energy. Okay, so let's do another example. Here we have an underdamped harmonic oscillator. So we have a simple pendulum, this is the oscillator, with a length L equals 1 meter, which is set into motion with small oscillations. After 5 minutes, the amplitude has decreased to exactly half of its initial value because of air resistance. So we're going to do a few things here. We're going to calculate gamma, that's the damping coefficient, and then we're going to calculate the percent difference between omega naught, that's the undamped frequency. In other words, that would be the frequency of the oscillations if there were no air resistance, and omega prime, which is the frequency with damping, with air resistance. So what's the difference between those two? So let's work it out. Okay, so first, let's take a look at the amplitude. Remember, for a damped harmonic oscillator, the amplitude is given by A of t equals A naught times e to the minus gamma t. So in this case, we're told that the amplitude is exactly half of what we started with after 5 minutes. So that means on the left side for the amplitude, I'm going to have exactly 1/2 of the starting amplitude. And then on the right side, I'm going to have A naught times e to the minus gamma t. So again, this is amplitude cut in half. So whatever the initial amplitude actually was, it doesn't matter because that drops out. And then next, we'll take the natural log on both sides. So we have the natural log of 1/2 equaling the natural log of e to the minus gamma t, which just gives us minus gamma t. Now in this case, we're interested in finding gamma. So gamma is minus natural log 1/2 over t, and in this case, we have to put in the time it takes, which is 5 minutes. So we have minus natural log 1/2 divided by the time, which is 5 minutes. 5.0 minutes is the same as 5.0 times 60 seconds. So gamma is measured in inverse seconds. And if you crunch the numbers, it comes out to 0.00231, which we'd want to round to 2 sig figs to be 2.3 10 to the minus 3 inverse seconds. So this is what we call the damping coefficient. And it's really small, meaning there's not really that much damping. So let's do some more work on this. Remember angular frequency? So if we have a simple pendulum and there's no damping, so no air resistance, in other words, then we have what's called omega naught. that means no damping. And this is given by the square root of G over L. So go back to the lecture when we talked about simple pendulums. This is the angular frequency, assuming there's no damping. So this would be the square root of G, which is, assuming the pendulum is on Earth, G is going to be 9.8 meters per second squared, and then L is 1 meter. So this works out to 3.13 inverse seconds. So about 3.1 inverse seconds. So notice how, in this case, if we compare omega naught to the damping coefficient gamma, it's much, much bigger than gamma. So we're in this underdamped territory, which is what we knew from the outset. Okay. So that's a simple pendulum, no damping. With damping, okay, the angular frequency is what we call omega prime, so it's different from before. And omega prime is equal to the square root of omega naught squared minus gamma squared. Okay, so then what's the percent change in that angular frequency when we introduce damping? So in other words, here's what I want us to calculate. Percent change is going to be given by omega prime, that's the frequency with damping, minus omega naught, that's the frequency without damping, over omega naught, and then times 100 makes that a percentage. Okay, so to simplify that expression a little bit, we can write this as omega prime divided by omega naught minus 1 times 100. And let's plug this in for omega prime now. This is going to be, so we have the square root of omega naught squared minus gamma squared, that's omega prime, divided by omega naught, which I can write as the square root of omega naught squared. Okay, then we subtract 1, and then we multiply 100. So what we have is the square root omega squared over omega naught squared over omega naught squared is 1. And then we have gamma over omega naught, which we square here. So that's what's under the square root. And then we have minus 1 times 100. That's going to give us the percent change we're looking for. So, okay, let's put in what we know. We have the square root of 1 minus, okay, gamma, if we go over here, was 0.00231. So we have 0.00231 inverse seconds with 2 sig figs on that. And then omega naught, if we go up here, was 3.13 inverse seconds. We're squaring that whole thing. And then we're subtracting 1 and then multiplying 100. So if you calculate this, it's absolutely minuscule. It's a tiny, tiny percent change. The number is minus 0.0000273%, or minus 0.00027% with 2 sig figs. So tiny decrease in frequency compared to the undamped frequency in this case. So here's the takeaway point of this. If the damping is small, okay, and that means that omega naught is a lot bigger than gamma, as we had here, the frequency of the oscillations is not really going to be that different from the undamped frequency. So the frequency of the oscillations is not very different from the undamped frequency. In other words, omega prime is pretty damn close to omega naught, which is why all this time when we've done experiments with pendulums and measuring their period, we were able to get away with ignoring air resistance because, again, as long as the damping is small, it doesn't have a huge effect on the frequency. Okay, so that takes us to driven oscillations. Now, so far, we've only been considering oscillating systems that move in isolation once they're set into motion. So, in other words, there's no outside force acting on the system once it's set into motion. So, for example, if we have a pendulum, I could set it in motion like this. I could just sort of displace it from its equilibrium position and then let it go. And so once I've set it in motion like that, it's just oscillating back and forth in isolation. Okay, so that would not be a driven oscillation. On the other hand, think about how you push a kid on a swing. A kid on a swing is just like a pendulum because you basically have a mass hanging from some fixed point. But the way you do it in that case is every time the kid comes by, you give him a little push. So actually, that's a driven oscillation because you are providing an outside force on the system that pushes on it as it oscillates. Okay, so that would be an example of a driven oscillation, is pushing a kid on a swing as opposed to just letting the pendulum swing back and forth on its own. So that's the sort of situation we want to consider now. So in addition to the restoring force, which is given by Hooke's law, and the damping force, we're also going to consider some kind of external driving force, some outside force acting on the system. So another example of what this could look like is if we have a mass connected to a spring. If there's like a motor that's pushing the spring back and forth, that would be an example of an external driving force. So let's consider an external driving force, F external, which has this form. Okay, so it's given by F0 times cosine omega t. So in other words, we're driving the system at a certain frequency, which we'll call omega. Okay, that's what we're dealing with here. So if we use Newton's second law, if we apply Newton's second law to this situation, the net force in the x direction is m times ax. Now we're going to have minus kx, that's the restoring force from the spring. We have minus b times v, that's the damping force due to air resistance. And then we have the driving force, which we add to that. So we have all three forces, and that equals m times ax. Okay? So just like before, we'll remember that the velocity is the first derivative of x with respect to time, and the acceleration is the second derivative of x with respect to time. So we'll make those two substitutions. And then to write this in kind of the standard form, we're going to take all these terms on the left-hand side and move them over to the right-hand side. So we're going to subtract this guy, and we're going to add these two terms to both sides of the equation. So we'll have m times the second derivative of x. and then plus b times the first derivative of x with respect to time, plus kx, and then minus f naught times cosine omega t equals 0. That's sort of the standard way to write the differential equation. And just to keep track of everything that's going on here, this term is just mass times acceleration. This second term is our damping force. This third term is our restoring force. And this fourth term is our driving force, which again, we're just assuming has the form f naught cosine omega t. If you add all that together, you get 0. So if we want to understand how a driven oscillator moves, then we need to solve this differential equation. Okay, so fortunately, we're not going to go through how to solve this equation. I'm just going to tell you how it works out, okay? Because the math gets a little complicated, and to really understand how this works, you need to take a course in differential equations. So I'll just tell you the result, okay? The solution to this differential equation has two parts. Okay, we have what's called the transient solution, and then we have what's called the steady state solution. Now, the transient solution is exactly the same as what we had before for the damped harmonic oscillator. So let's take a look at the transient solution down here. It's x of t is equal to a times e to the minus gamma t times cosine omega prime t. So we've already seen how that works. This is describing an oscillation that dies out over time. So eventually the transient solution is going to go away because, again, these oscillations are dying out over time. And if you want to understand exactly how the transient solution works, you're going to need to know what the initial conditions are. In other words, what is the position and the velocity at t equals 0? Now the other part is called the steady state solution. So after the transient solution dies off, the system is going to be oscillating with a constant amplitude, which we'll call b, and it's going to be oscillating at the driving frequency, omega. So in other words, whatever frequency you're driving the system with, that's the system it's going to be oscillating after you let the transient solution die off. So the constants b and phi that you see in this equation here are independent of the initial conditions. So it doesn't matter how you start the system off. The transient solution will die off after some amount of time, and you're only going to be left with the steady state solution, which depends on the constants b and phi. And these two constants don't depend on the initial conditions. So here's our steady state solution. X of t is equal to b times cosine omega t plus phi. Again, we're oscillating at that driving frequency, omega. And so that takes us to the idea of mechanical resonance. So the question is, if we drive a system at a certain frequency, how big of an oscillation are we going to get? Are we going to make the system oscillate only a little bit or oscillate a lot? Well, that depends. The final amplitude of a driven oscillator is going to depend on how close the driving frequency omega is to the natural frequency of the system. So remember, if we have a mass on a spring, the frequency omega naught, the natural frequency, is going to be root k over m, as an example. So let's put this on a graph. Let's take the vertical axis to be the final amplitude we get, so how big of an oscillation do we get? And let's take the horizontal axis to be the driving frequency. This is the frequency that we're driving the system at. So what you're going to find is you get this curve where for very low frequencies, the final amplitude is really small, so you're not really getting the system to respond at these low frequencies, but then it shoots up and then it peaks somewhere, and it turns out it actually peaks at the natural frequency of the system. So in other words, if you drive the system at its natural frequency, you're going to get the biggest possible oscillation. You're going to get the biggest final amplitude. But then if you go past that and you go to higher frequencies, then the final amplitude falls off again. So that's the idea behind resonance. The largest possible oscillations occur if you drive the system at its natural frequency. And we call these different curves that you see on the plot resonance curves. And the different curves correspond to different amounts of damping in this case. So if you have a lot of damping, then your resonance curve is going to look kind of wide with a very small peak. If you have less damping, then your resonance curve is going to look more narrow with a higher peak, okay? But in every single case, again, the peak is going to be located at the natural frequency of the system. That's where you get the biggest possible oscillations. And I'm going to show you a video that I stole from MIT just to give you a sense as to what this looks like. So you're going to see a driven oscillator. It's going to be a mass connected to a spring, but it's going to be driven by a motor. Okay? So let's take a look at what happens when we drive the mass on a spring with a motor. So right now we're driving it at kind of a low frequency. So we're below the resonant frequency, and it's not really responding very much to that. The oscillations are very small. Then if we crank up the frequency a little bit, so we're at the resonant frequency, and then we get really big oscillations, okay? And then if we crank the frequency up even more, and then go past the resonant frequency, then the oscillations are going to be small again. So the point is, if you drive the system at its natural frequency, you get the biggest possible oscillations. If you drive it at a different frequency, you'll get smaller oscillations. If you want to see this video again, by the way, I left the link at the bottom of the slide here, so you can watch that on your own time if you like. And credit goes to MIT for making that video. All right, so we can actually demonstrate the idea of resonance using a simple pendulum. So here I have a mass connected to a string, and basically I can introduce a driving force just by shaking the string back and forth like this. Now, as we'll see, depending on the frequency of my driving force, how fast I choose to shake it back and forth, I'll get a different response, okay? So for example, if I shake it back and forth very quickly like this, the pendulum mass is not really responding that much to what I'm doing. Okay, so in other words, the driving frequency is way above the resonant frequency, and it's not really responding to that. So if I decrease the frequency of my driving force, and shake it more like this, now I'm getting a very large oscillation. So this is what resonance is all about. If I drive the system at the right frequency, I can get a very large oscillation. So another example of mechanical resonance is something that I showed you at the very beginning of this lecture in the very first video from chapter 14, and that's the failure of the Tacoma Narrows Bridge. So this is a bridge that was built in Washington back in 1940. This bridge collapsed, and this is a video that I showed you before, which is showing what happened just before the bridge collapsed. So you can see that it's oscillating wildly with huge oscillations. What's the reason for that? Well, the wind provided a driving force that was near the resonant frequency of the bridge. And as we know, if you drive a system close to the resonant frequency, you'll get really big oscillations. In other words, very large amplitudes. So this is something that the engineers didn't account for. They didn't account for the fact that the local weather could actually drive the bridge to vibrate at its resonant frequency. And as a result, they didn't see what could happen to make this catastrophic failure. So these oscillations were so large, the amplitudes were so large that eventually it just destroyed the bridge altogether, caused it to collapse. And there are other examples in history of bridges that were built that get driven at this resonant frequency, and they have this unexpected large oscillation happening that is unintended and actually you don't want. So for those civil engineers out there, you need to know about mechanical resonance And you need to know that certain structures you build can resonate in unexpected ways, and you better account for that. Okay, another example of mechanical resonance is the fact that we can shatter a glass using sound. So I'm going to show you a video of a very loud sound coming out of this opening, very close to a glass. It causes that glass to vibrate at a certain frequency. And again, if that frequency is close to the resonant frequency of the glass, then the oscillations will be very big and eventually can cause the glass to shatter. So this is what that looks like. So it's a similar idea as the failure of the bridge. We have this driving force that causes the glass to vibrate at a certain frequency. It's close to the resonant frequency of the glass, so the oscillations are very big, very large amplitudes. And if the oscillations are so big that the glass can't withstand it, it will just shatter. So the last thing I want to touch on here is the equivalence between different oscillating systems. This is the idea that you can have two different systems that oscillate that look very different on their face, but they're equivalent in the sense that the equations describing them look exactly the same. They have the same mathematical form. So we've seen a few examples of this already. We have the mass on a spring, and then we have the pendulum. And although these look like very different systems, at least on the surface, when we drill down to the equations that describe their motion, they actually have the same mathematical form. And so there are a lot of other examples of equivalence between different oscillating systems, and you can take this idea really far, actually. But I want to show you an example of an LRC circuit. Okay, so if you take Physics 46, you may learn about LRC circuits at some point in the semester. This is an example of an electrical circuit where we have something called an inductor, which is labeled as L here, something called a capacitor, labeled as C here, and something called a resistor, which is labeled as R on the diagram. And then we have some kind of power source, which gives the circuit a certain voltage, which we'll call Vs. Now, if I write down the equation that describes how electrical charge is moving around in this circuit, this is what it looks like, okay? Now, let's not concern ourselves with the details of this, okay? Because if you haven't even taken electricity and magnetism, you don't know what L, C, and R actually mean. But just look how the mathematical form of it is exactly the same as the equation for a driven mechanical oscillator. So remember, if we have a mass on a spring with some damping and an external driving force, we have this differential equation that describes the motion. So although the constants are different, like we have M instead of L, and we have B instead of R, and K instead of C, the form of the equations is identical. The mathematical form is the same. So in other words, if I know how to solve this equation, which is describing a block moving back and forth, then I know how to solve this equation, which is describing something totally different, electric charges moving around in a circuit. And that's kind of the amazing thing about equivalence between oscillating systems, is two systems that look very, very different are on some level the same thing, at least mathematically. And you can take everything you know about the solution to one of those and apply it to the other. So that's all we're going to do for chapter 14, and that's going to be the end of this video. So I'll see you in the next one. Until then, be safe, be healthy out there. See you later.